All right. So, hello everyone and welcome back. So, today we will be discussing yung ating Hooke's law. So, it is one of the most important laws when we want to understand the behavior of springs. No. And I'm not, we'll be going through four ways on how you can get the equation ng ating Hooke's law. So, I will just treat it as three since yung unang way is really just through observation and understanding, or an empirical method, so to say. So, without further ado, let us begin. Hooke's law. Of course, the proponent is none other than Robert Hooke himself. And ito yung ating first method actually. So the irony of this is that si Robert Hooke mismo, he did not derive the law in a modern theoretical sense. Again, Robert Hooke was an empiricist. No. So in this sense, no, he discovered it experimentally. No? And ayun nga, he attributed an anagram to this. So, little trivia lang. He attributed an anagram. And this goes as follows. Sulat ko lang and then I'll try to explain it. Yan. I think I did it right. Yan. Ito yung anagram. Not sure on how you would pronounce it, but in the later years, ano, it was later revealed. Ito yung statement niya. Ut, tensio, sync, vis, or V, or yeah, yun. Ito yung statement niya. And this literally translates into as the extension, so the force. This is the basic principle of springs. No, as the extension, so the force. Let's say I have a spring. Yeah. Not really the most fancy spring, but let's say na meron siyang displacement. No, there is a change in position. Now, masasabi natin that the more that you pull the spring, the more it stores energy. And the more energy it has, the more force it can dissipate. No. So we can just say, no, so let's put something here ano, to signify the direction kapag binalik natin yung spring. We can say that in mathematical terms, masasabi natin na yung ating force is just directly proportional to the change in position or yung ating displacement. Now, we have a proportionality. And again, if we want to make it an equality, how do we do that? We just introduce a proportionality constant. In this case, yun yung ating spring constant, which is K. No? And gawin natin siya negative. So why the negative? It is because of Newton's third law, which states that for every action, there is an equal and opposite reaction. So, di ba, pupunta dito yung ating spring. There is a force that would counteract it, which is ito. No. So, yan din. Hence, it is negative. Ayan. So, this is the first way on how we get yung ating equation of the Hooke's law. Ano? So, again, mostly through empirical methods. Ayan. Now we move on to uh, something more conventional, something more or something more orthodox, no? And we use the concept of elastic potential energy. I did mention before that the more you pull a spring, no, the more energy it stores. We use the same concept here. However, we make the assumption that yung force na yun would be conservative. And that conservative force is basically a form of potential energy. No. So we can derive it through this. So let's say na yung ating force, no? And again, as time goes by, uh, yung ating physics uh, aspect, yung pinaka-subject ng physics is also nag-evolve. So during this time, we have Newton. No. And again, he used calculus, which is basically the math of change. So we use a derivative. It would be, in this case, it is the change in potential energy with respect to the change in position. No. So ito yung derivative niya. And again, for a spring, no, i-assume natin na yung kanyang simplest possible potential energy ay symmetric. Therefore, quadratic in displacement. No. And yung, of course, yung kanyang force is always zero at equilibrium. No, equilibrium entails that the force is zero. It is not moving. So we can state that yung ating potential energy, gagamitin yung kanya equation as a function of x. Yung equation natin ng potential energy, it is 1/2 k. In normal terms, this would be E, but we use x squared. No. Yun. Now, we take the first derivative with respect to x. So we just use the power rule and cancel na to. Therefore, yung ating derivative ng u with respect to x, that is equal to kx. And what have we noticed with this equation? Is the same as our initial equation. Yun. So, if you want to derive this equation in simple terms, ito na yung way, most conventional way to do it, since ito yung ating pinaka area of interest. No? For the third way, we're going to something a bit more fundamental and molecular in aspect. Speaking of molecular, we are talking about our interatomic forces. No. Let's say I have a solid. For example, a cube. Looking at it at a microscopic level, yung mga solid natin, they still have molecules bonded together. And of course, yung ating molecules, they're comprised of atoms. And molecules are basically atoms that are bonded together. Which means if they are bonded together, there must be potential energy between them as a function of separation. No. So even though na magkakadikit sila, di ba? So ayan, let's say they're combined, hindi sila nagalaw, which means that they are bonded together. So yun yung basic explanation doon in the molecular level. No. And they're basically bonded by yung ating intermolecular or interatomic forces, which is basically yung ating fundamental explanation dito. And Ayun nga, since maliit yung ating displacement, no, we can state yung ating x to be, since yun nga, maliit, sobrang maliit yung ating displacement. Let's say we use a different variable. So let's say r minus r sub 0. So maliit lang siya. And based on this format, no, yung ating potential energy has a minimum. Ano, it has a minimum at the equilibrium separation. Ito yung ating r sub 0. No? And ayun nga, of course, yung ating net force ay 0. Which means that yung ating force or yung ating change in the potential energy with respect to the small displacement, that will be equal to 0. No. And with this, we can perform a Taylor series expansion, no, of u as a function of r. Of course, even though that they're bonded together, this still has potential energy. And when we generally do a Taylor series expansion, it's just derivatives. So we have the original function plus the first derivative no plus the second derivative and so on. No. Now, even though we performed a Taylor series expansion, our goal is not really to expand it, but rather converge it. No. So, ayun. Itong ating first term, set na natin siya into 0 since it's just for energy reference. No. And itong ating first derivative, we can also set this into 0 because it's a minimum. Yung ating force ay 0. No. And yung ating second derivative, iset natin siya into K. No, which is our spring constant. No? It signifies the stiffness, which is what we used here as well, but we're just explaining it at the fundamental level. Since yung ating R sub 0 ay minimum, that must mean that yung ating second derivative or yung ating K, which is a spring constant, is greater than 0. No. Which means that for a small value of x, yung ating higher order terms ay negligible na. So, yung ating pinaka-approximation, yung ating pinaka-value here is u of x. So, balik natin siya in terms of x. That is approximately 1/2. Yung sa ating second derivative, that is yung ating k. And itong ating r minus r sub 0 squared, ayun yung ating x. No? So, ayun. Ito yung ating pagkakakuha dito. Yan. This is the same. And this will eventually lead up to this. No? So, f equals negative kx. So that is how we expanded that equation and turned it into Hooke's law. No. So again, it might be complex in the sense that we are explaining it at the molecular level, but that is basically the explanation there. Ayun. And for the final way, no, since we are more inclined into mechanical engineering, we can't forget about yung ating mga stress and strain, no, which is a part of our continuum mechanics. in which we consider yung ating geometry ng ating material. So, in this aspect, we are considering yung ating spring to be a bulk elastic material. So, we are considering it to be a rod with a length L with a cross-sectional area of A. And since it is undergoing force, we're going to assume it is a tensile force, which is tension. No. So again, we will use yung ating mga equations of stress and strain. So for stress, it is equal to the force over the area. And yung ating strain, that is equal to the change in length over the original length. No. And since we are dealing with infinitesimally small strains, no, the same with our interatomic forces. So yun yung pinaka explanation niya is there is infinitesimally small strain na nangyayari in which we can correlate our strain, ano, or our stress rather, no, yung ating stress to be directly proportional to our strain. And again, to make this into our equality, we have to consider yung ating axial loading. In other words, yung ating Young's modulus, E. No. Now, we will just use some definition here. No. So, again, yung ating force over area, that is yung ating sigma. No, or yung ating, yes, I think, tama ba? Yes, yung ating sign ng stress. No. So, it would be yung ating, or I think this would be raw. No. So, ito yung ating Young's modulus. No. And then, yung ating strain. Delta L over L. Ano? And solving for F, we would end up with this equation. Yan. Ayan. In which, itong expression na to, Young's modulus times the area over L, ito yung ating spring constant K. Dito sa part na to, it is more complex because we are considering the material used as well as its geometry. The material used is signified by our Young's modulus, no, and its geometry signified by the area as well as its length. And ito ating delta L, that is basically the displacement. So we can say na yung ating force is equal to K delta L. Or if you want to respect Newton's third law, put the negative. Ayun. So I guess those are the ways we can compute yung ating Hooke's law. Or we can derive rather yung ating Hooke's law. As you may have noticed now, marami tayong paraan na makuha yung ating Hooke's law. That is because this equation is basically universal. No. So we can get the equation empirically. We can get it through quantifying the energy, the potential energy. We can get it through analyzing the intermolecular forces at play. No? And if we consider the material used, we can also compute or solve this equation. No. However, yung kanyang pagiging universal is also a downside. Ano? So it's kind of ironic because in the end, yung ating Hooke's law is just a linear approximation. It's just a linear approximation. which means that may breakdown siya at a higher level. So, what do you mean by higher level? Let's say, yung ating spring, nagkaroon ng large displacement. In the real world, sa tingin nyo, anong mangyayari sa ating spring? No. So, it would break. No. When it undergoes plastic deformation, considering the material, yung spring natin nasisira. And that is not really covered by Hooke's law. No. And one other way that it would become obsolete is that when we consider the higher terms in our Taylor series expansion. If i-consider na natin yung higher order terms, yung ating linear approximation would start to break apart. So basically, hindi natin masyado nako-consider yung real conditions na nakaka-affect sa ating spring. And, ayun. But still, it is a very good approximation still because most of the time, we are designing springs to undergo high loads, ano? So, to undergo high amounts of stress. So, hindi siya basta-basta nasisira. And that is where we can still apply Hooke's law. And, ayun. So, I think that would be it for this video. No. So, ayun. So, I hope you have learned something at least, ano? And if I want to make another video regarding sa ating sa ating vibration, then I would likely do so, but it would be another time. No, since in nga revision ng DE natin, and I really haven't touched much up yet dun sa ating DE. So ayun. Thank you guys for listening. No, I hope you have learned something again. Thank you guys, and I will see you next time.